Aí, se atualizar o YouTube, aí provavelmente já vai estar aparecendo na tela do Meet. Atualiza aí pra gente. Tá? Já tá aparecendo você, né? Por que tá aparecendo eu? Porque eu tô compartilhando a tela do Meet aqui. Tipo, a tela que eu tô vendo, você tá vendo também. Só que agora eu vou fazer o seguinte. Vou compartilhar a apresentação. Aí, em vez de você, vai aparecer eu e você e a apresentação. E agora, só a apresentação, correto? Aí, depois que eu posso fazer aqui, ó. Deixa eu ver aqui se existe alguma forma de mudar isso aqui. Pronto, apareceu. Só que demora a carregar, né, no YouTube. É o delay que tem, né? Fica diferente. Aparecendo. Beleza. Aí, eu queria deixar só a apresentação, mas deixa, tá bom, sim, tem nada não. É, aí, aqui. Agora eu não tô vendo mais a tela do Meet, tá? Eu tô vendo só a minha tela aqui. E esperar um pouquinho, pá, pra eles confirmarem lá, organizar aqui as coisas. Ah, beleza, eu vou simular que ele já disse que poderia começar e eu vou começar, certo? So, good morning to everyone. My name is Michel Lopes Bastos, and today I present for you my PhD thesis entitled DiagNose.AI, a novel explainable artificial intelligence framework for the identification of Candida spp from volatile organic compounds using electronic nodes. My advisor is Professor Dr. Leandro Almeida, and I have a special thanks to Professor Dr. Margaret Powerfetcher to supervise me and help me during my period at the University of Cincinnati. Thank you so much, Maggie. Here you have the guide of this presentation. First of all, we talk about a brief contextualization from the problem, the justification and motivations, the objective, and how the development and methodology was conducted, the main results from this project, the conclusions, and the future directions for this work. Okay. So, first of all, we need to understand a little more about the major problem that motivated our work. When we think about health, one of the most critical challenges in this area is the diagnosis of infection disease. In this case, the speed and the accuracy are so determinant to the patient outcomes. In this sense, invasive fungal infections, especially those caused by Candida spp, represent precisely this scenario. From this context, we can emphasize the main challenges and motivations from this thesis. Some studies show between 40 and 6% of the deaths in intensive care units are caused by some kind of fungi. Within them, 80% of the fungal infections are caused by some kind of Candida spp. Another important data is related to time. It takes 2 to 7 days to identify any fungal infection in this scenario. In addition to this, we need to understand a little more about the blood culture. Is the currently gold standard for laboratory diagnosis of candemia. However, this method has a low sensitivity, around 50 and 6%. And another important point is the low positivity of this method, varies from 21 and 71%, second studies related by beta. With this information in mind, it's possible to summarize the motivations in two main scenarios. What needs to be done in the result that can be achieved through the proposed solution. One of the things that we need to reduce is the time to identification of the fungi. With that, we have the increased patient chance of survival. Another important point is the try to reduce the cost of carrying out identification procedures. With this, we can have making the procedure more accessible for the population. Good example for that is the population accessed by the SUS, and we can create a solution that can be used for this kind of population. Another important step here is try to reduce the sensitivity problems in the identification. With this, we can have a more precise and reliable solution. Another important step is try to lower the barriers to extract meaningful knowledge. With that, we can make a standardization of the extraction process and explainability. Solving these problems or try to solve these problems, we can try again the health for the patient, and it can be leave the hospital and go home for your family. Based on this information, it's become clear that the identification process for this kind of microorganisms can still be improved. To address this gap, the analysis of volatile organic compounds emerged as a non-invasive approach for the identification of this kind of pathologies. In the context of computed science, we have the electronic nose. Is a powerful computational tool that can make the identification of olfactory signatures from biological samples and generate valuable data from our proposal. In this way, aiming to address all of these challenges by combining electronic nose, pre-processing techniques, artificial intelligence, and dynamic explainability tool, we propose the main objective of this work is develop and validate the DiagNose.AI, an innovative framework that integrates electronic nose box analysis, AI models, and a sample-based explainable AI to enable fast, accurate, and interpretable identification of Candida's PP microorganisms. So to achieve this objective, we develop the Diagnose AI framework. In the next sessions, I will show you how development and the methodology from this process was conducted. We divide the Diagnose AI framework in 5 main modules. The first one is related to the experimental protocol and data acquisition. Is how we make the acquisition of the data using the nose and our protocol. After that, using the data generated by the nose and the samples read, we apply the data engineer process. Here we execute some pre-processing techniques to adjust the data and generate the best input for the AI models. Another important step is the Vox mapping, where you get the information of the Vox identifier by each sensors and the Vox emitted by the candidates and make a match between them. The other important step for the framework is the predictive modeling, where you get the main AI techniques for the state of the art and training and generate and make the selection of the best AI model for the framework. And the last step is the explainable AI, where you build the shy ensemble method to turn the prediction generated by the models more clear and explainable for the final user. But how the process works as a general. Here we have the sample identification flow for all methods. And you begin has the collection of the material. Here it's important to highlight that we make two kind of experiments with a TCC control and blood broth. And after this step, the another step will be the same for this kind of experiments. So we have two kind of experiments, and the difference is the first step where you make the collection of the material, okay? And the next sections, I divide the experiments and the results using these two type of experiments. After the collection of the material, we make the mycological diagnosis in laboratory and the labeling process, where you put the name from each sample in the petri dish in the tube. And after that, we make the reading of the samples using the nose and collect the data and generate the dataset files and apply this to the AI techniques and further make the analysis and the prediction of how Candida was in the sample. And the final step is make the explainable AI report that I will show you the Shine sample method created for this purpose. But how the experimental protocol works and the data acquisition works in this project. The first thing I will show you is the device. One of the NOs that we use in this process was the sweet case NOs. And this NOs is composed by a physical device, a computer system, and a collection protocol. Was used for the culture experiments, and it's composed by some PTFAA components to prevent the vox from sticking to the surface of the device. We have a sample chamber where you put the pretty dishes for the analysis of the vox. It's a YouTube for the analysis of the vox. And we also have activated carbon filter here to make the purge stage. And inside that, we have 7 gas sensors and another 3 environment sensors to make the read of the fox when it's aspirated um, graph for the ANOS device. Okay. Um, and here we have the another ANOS used for the blood group experiments. This one was built exclusively through experiments in USA. We- Não, calma. Mas eu não fiz nada, só tô sozinha. Tava assim, aí parece. Mas não tá mudando, tá mudar aqui, ó, geral. Você vai falar do outro lado também, mas eu tava falando aqui. Uh, because we need a more suitable equipment for the international transportation and to avoid problems with the custom, because the previous node is so large and seems like a pump. And we need a more suitable device to this kind of purpose. But it's composed by 5 gas sensors and 3 environmental sensors also. Best for transportation, as I said, has a artificial pump to make the breath of the vlogs in the practice, and also composed by PTFA components. These are made with PTFA to the same purpose with the previous NOS. But how the nose works? Here we have a little analogy, make a comparison between the human body and the fungi. And the human body can exhalate some compounds in the air in different ways by the speak, and the fungi also emit compounds in the air. Are different types of compounds, but they both can call it volatile organic compounds or just VOX. When this VOX touches the surface of the gas sensor, this will be generate a resistance, and it's this resistance that we use for the AI model make your analysis. Okay, here you have the example of TGS 813 generated by some blocks. And another important thing you need to know is how the protocol to the acquisition of the data works. Okay, here you have an example, and each cycle is composed by these three steps. The first one is the aspiration step, where you make the breath of the vox inside the petri dishes. After that, we'll have a wait for stabilization and have a time to the vox make the interaction of the sensors inside the chamber. And after that, we conduct a pouring stage where you um, put filter R or inject the filter R in the chamber and forcing the chamber to be cleaned using this kind of equipment. And after that, we make wait time to begin the next cycle. Okay, this step is executed by 10 or 40 times, more or less. And here we have some examples from the samples used for the experiments. The first one is an example of Candida albicans. You use it for the culture data set. And the second one is the Cryptococcus delphinus sample. You use it for the blood growth experiments. Okay. But how the data collection occurs in the sampling handling protocol? Here is an important step also because you need to know how we handling the samples and make the process of collection of the data using the nodes. We divided that in the blood broth handling protocol in the ES, and they both have similar steps, but the first steps are different for the both. And I will show first the blood broth steps and after the ES steps used for this kind of protocol. Okay. For the blood broth, after the blood culture and sample labeling, and they were separated in a cooling chamber at less 4 degrees. After that, to bin the readings, it was necessary to wait for the sample to reach room temperature. For after that, we can use the sample in the reading stage. Okay. In the ES sample or culture samples, we make something different. We put the fungi in a pretty dishes and make a cultivation of the fungi in these pretty dishes. And after that, we wait for different times of growth times, 1 day, 2 days, and 3 days, for we analyze the different kind of vox emitted in each of these days. Okay, um, so we make the culture and wait this culture growth in different kind of times. For just after that, we make the aspiration of the fungi in the BSC. But before we start the aspiration time and the protocol of collection, we make a sterilization of the BSC with UV length. In this case, alcohol is not recommended and to avoid the votes from the alcohol interfering with the experiments, okay? Because that we just use UV length for make this sterilization. After that, we use the samples in the nose, run the protocol, and after we have the samples, the CSV files with the resistance of the vox emitted by the candidates, and after we have all the files, we make the dispose the material in a safer place. Okay, so this is how the rendering protocol works in the both scenarios. And another things, important things we need to know is about the data engineering, and that includes the pre-processing data for the files and the input to the model. Okay, so after we have the main hot data files in hand, we can make the data extraction of these informations. And the first step is make a match of the cycles. Generally, the cycles may come in different sizes. This is due to the readings errors or different kind of setups defined in the collection protocol. Okay, and we have to restructure these cycles so that they all have the same length in this step. To the final model can be read correctly this information. Okay, and after that, realize step to remove name value result lines, any other kind of um, unnecessary data to make the concatenation of the sensors per cycle. Note that the sensor one here are um, joined side by side with the your data in the same line. Okay, so we have the same line of the sensor one to this cycle in the same line. You need to make this hex structuration or converting the readings into cycle as this way to the final model have the correct input for your analysis. Okay. And after that, I will show you just the step conducted for the blood birth experiment because it's more complex than the process executed for the culture experiments. Okay, I will show the reasons now. For this step, we apply an oversampling strategy to create synthetic samples with the same patterns that the real ones to verify if this could bring benefits to the models without losing reliability. So due to unbalanced data, we need to apply this strategy to check that if you have some benefits with this application. And another important thing that we did was check another kind of models. In the culture data set, for example, the culture experiment, we just use time series model. Yeah, of this step, we just make that. And in this case, we also use non-time series models to check if you can have a better performance with a low computational power or cost. Okay. So in the final, we have four kind of results. The result with the original data and non-time series models and oversampled data and time series models also. And to select the best model, we will use some metrics and statistics informations. And after that, we can choose the best model for the final application. Here an example of the final database for the culture experiments. This example is for the training set. And here we have the value of each sensor side by side. And the last one is the label or just the species categorized and divided in some categories here to make the prediction and with the correct input. But how the Shine symbol was built, how the Shine symbol explainability architecture works in this project, I will show you the next section. Here we have the framework main process for the predicting and explaining the results after we have the data set has been generated and the final model has been selected. Okay, so in this case, we already have um, um, data set structured and a final model built and trained. To do that, the first thing that we need to do is read the new sample using the NOs. After that, we make the restructuring data as I show you in the data engineer process. And with that, we will have the main input to the final model, and the model will be made your prediction. You do your prediction, and transfer this information for the explainable method that we call shine symbol. And after that, the shine symbol will highlight the most relevant sensors in prediction according your methods. Okay, so to explain better this, I will highlight this context for you to understand better how these steps occurs. Here we have a line chart that represents each of these lines represents the resistance of generated by each of the sensors to the vox emitted by the candida, and we make the extraction the cycle from these readings according to the pre-processing technique that I showed for you before. And this cycle will be used for the final model to your prediction and for the Cheyenne sandbox also. Cheyenne sandbox you will receive this input and the output of the model. And we use that for make your decision about the main features that the thing that is most important for the prediction. Okay. Each of these methods will highlight the characteristics that they believe that the model considers most important for the prediction process. For example, the GradCam will highlight the sensor green, yellow, and red here, and lime the same thing, green, yellow, and red. But the shape will highlight the green, blue, and the red. We have a discordance here, but a disagreement here and agreement between these both models, these both methods, and have the same features selected but in different orders. And this can be bring for us a little difference in some metrics that I show for you in the next sections, but it's not a concern for us. Okay. After that, after each sensor, after each method select the sensor that it's believed that most important for it. We make a hex structure important by sensors for have more um, clear information for the final user about the transparency of the method. And we have exhibition similar with the original reading. Okay. And with that, we run this method 3 times to have a redundancy in the answers. And after that, we apply the majority voting strategy. In this case, the sensors with the high number of votes among all the methods are selected. For example, here, the GradCam and the Lime select the same sensor as the most important in your opinion, but the SHAP select another sensors set as for as most important for your opinion. But in the final, because we collect the max voting for each one. The S4 are don't have the most votes in this case, and the S1, S3, and S4 are highlighted as the main sensors for our proposal. Okay. Another important step here to highlight is the mapping strategy. And we receive the most relevant sensors generated by the Cheyenne symbol method. And in this case, we make a mapping sensor box with the funga box. But how this works? In this step, we use a data set that created with information of the vox identified by each sensor and the vox emitted by each candidate. So this step was developed to show that there is a logical sense in the model's prediction, demonstrating that there is a correlation between the selected sensors and the predicted candidate. So in this case, the sensor 1, 4, and 5 are identified methano, decane, hexano, and the candidate A emitted this kind of components. this kind of volatiles. So, and with that, we can see that the model was correct because make the correct prediction based on the sensor selection, the sensor behavior, and the Candida Vox emitted. Okay, so you can make this correlationship between and this information. And after that, we run the next step related the textual report and the compared data. The textual report will summarize all of the information highlighted in the previous step in a text way, okay? And the compared data will get the current reading and compare with true samples from the dataset and to the user check if these patterns are the same between them, okay? And the last step was validation with final user to check if the usability of the method are good for the final user. And about the results and discussions, we will highlight the main points of this project and the main archives of this project, outcomes. So the first thing we want to highlight is the two database created for for these experiments. The first one is the culture database, generated here at UFPE, and the second is the blood growth data set generated with the partnership with UC Medical Center. Okay. The first one was created with the suitcase nose, and the second one with the prototype nose. And the first one, we work with Candida albicans, Glablara, Melon, Cadamia, Cruzi, and Parapsilosis. In the second case, we use Glablara, Parapsilosis, a union of Glablara plus Parapsilosis. Here we combine the Glablara and the Parapsilosis to also access the possibility to cross-contamination information, okay? We also use non-candidates to make the database more robust. Check has cryptococcus and negative samples, and the Candida albicans also was used, okay? So, to divide these results, I divide the informations in two scenarios. The first one is related the ATCC culture experiments. The second one will be related the blood broth experiments. So here, most of the models don't perform very well in the model test results. It's important to highlight here that this stage is the test phase when the model see the data that it don't see before, and this information is so important because it's not the data from training nor validation, is the test stage. This data, the data used here was new for the model, and it's more similar with the final environment that the model will use. Okay. In this case, the most of the models don't perform very well, but among all the models, in sample time was one of the performed best in all metrics, including the time. But although voice ensemble had a better time here, the difference between them is small. So 1 second is so fast yet. And how the statistical analysis was conducted in this case? So for the statistical evaluation, a literature research was conducted to identify which tests would be most suitable for our problem. In our case, because our problem has fewer than 10 models, the Shapiro test was selected as a normality test. Normality test. It's so difficult and say this word. Um, and since all of the models followed a normal distribution, the Kruskal-Wallis tests were selected for the statistical tests. testing, and as a consequence, was followed by the named test horizontal evaluation. Okay, but how was the main hypothesis that I apply in this case? The first hypothesis is that all the models have relatively equal average in terms of classification accuracy. And the second hypothesis is at least one the models differ from the others in terms of average classification accuracy. And applying the cross-color test, we have a Lopes value and being less than 0.05. This demonstrating for us that with 95% of confidence and that there is evidence to reject the first hypothesis. In other words, at least of the models differs from the others in terms of average classification accuracy. Okay? To comprove that, we apply the memory post-hoc test, and here you can see the difference between the inception time and TSCFC from the other models selected. The second scenario is related to validation with blood broth, as mentioned before. And here we have four results. Run results for each kind of experiments. We carried out experiments with time series and on traditional models and with oversampling data and with the original data without oversampling. Okay. And for the oversampling data, in time series, we have the best models, the Canigborn time series, with values above 90-70%. And for traditional models, we have the CVC model with the best performance between all the others. Okay? And without oversampling the original data, we also have the Canigborn time series, which has the best model between the others. And in the traditional techniques, we have the random forest has the best models with values above 95%. Another important thing that we conducted was experiments seeking to evaluate each metric by species. And for this example, we used the results from the random forest at its performance better than the traditional methods. So here we have some low values for the cryptococcus and negative samples, but this can justify it by the number of samples that they have in the original data. Okay, because that we it's a good thing applying the oversample strategy. And in this case, we apply another statistical analysis, sorry. But here we try to analyze another thing. For, for this new statistical evaluation, we use different tests due to the new nature of the problem with different evaluation groups. Okay. In this case, we apply the Shapiro Wilk for check the normality of the distributions. And when the distribution is normal, we apply the parity test, and when not, we apply the Wilcoxon strategy. And that indicate with models who are significantly impacted by the application of oversampling. And this chart show for us in this red line and represent the confidence interval, and models with bars above this interval were not significantly affected by the use of oversampling strategy. So we have just three models with bars above this line, and the other models can be used the strategy of oversampling without any concern. Okay, so we have good news here because we have a lot of models and the best models above this bar. But another important step here is know how the shy ensemble method and DiagNose tool was evaluated. We have five kind of strategies here. The first one is a direct comparison, and we qualify the level of agreement between the three shy symbol methods. Another step is the ablation study, when we try to understand the influence of each method on the results of the ensemble. We remove one method using the in the shy ensemble and analyze the result with this remotion. Sensitivity analysis, when you introducing Gaussian noise in the original test instance to check if this can be changed the results. The performance, which analyze the time from archive your results and return the information about the features. And a usability test, when you apply a Nielsen heuristic to specialists and get some feedbacks. Okay, but here we just will highlight these three last steps during the time. The sensitivity analysis. Here we have some good values, but a low value for the cattle tau. The cattle tau metric measure the level of agreement and disagreement in the ranking order of the list. As I show for you in the explanation from the shy ensemble method, we can have different orders in the results, and this can change the kernel tau coefficient for a low value. Okay, and this low value is explained by the Java card index measure the similarity between these sets, the groups, and the overlap coefficient measure, as the name suggests, the overlap between the groups, the sets. Okay, and we just have a low value here in the kernel tower experiments for the blood growth. Has the performances, regarding the performances, the sharp method will be a barrier for us. Notice that when you don't have the sharp method included in the assembly configuration, we have good times for results. But when you have the sharp method, the time significantly increasing and when it was used. And for the final applications, replacement is being considered when we need to try another method to replace the sharp method. Okay. And the final evaluation for the shine method, we have the application of a high fidelity prototype. In this case, we applied a usability questionnaire based on Nielsen heuristic to 11 experts, and the response to be considered were whether the prototype met, yes, not met, no, or partially met with the risk of Nielsen. And the vast majority of the experts report that the risks were met with the risks, but some feedbacks was collected to refine the risk with the answers has partially with the users that answer partially for the risk. Okay, you get some feedbacks and use these feedbacks to improve our final system. So, and about our conclusions. Finally, the conclusions. We divide these conclusions in two main topics: the general contributions and the computer science contributions. In the general contributions, you have efficiency of over 97% of positive evaluation for the both case culture blood broth and culture and blood broth experiments. We have the possibility to reduce the diagnose time for this, and we're using this technology, using this framework. And another important thing is the possibility to make the application in resource limited areas through the areas accessed by the SUS here in Brazil or in countries with poor or low financial income. The computer science contributions is the methodological parent for the sensor-based system. We create a framework that covers everything from data collection to the results explanation. We also create an explainable method, our shine sample method, to multivariate time series. Um, it can be adapted to different domain in the future. We also create two novel data sets, one with logs using the culture experiments and another with the blood breath logs. It's so important to the future and create and expand these data sets. And we also have a scientific production and academic recognition with our first paper published on Scientific Report by Nature and titled Breaking We're using Candida SPP Detection with Electronic Nose and Artificial Intelligence. And this paper already had published, and we also have two another papers in under review in some IEEE journals. By the future directions for this project, we have a lot of points here. It's good because the project can be scaled for different areas, and we have a lot of possibilities to do this project more bigger in the future. We can make a large scale validation and technology readiness. This is mean that you can apply this project and multi-center validation studies to expand the data sets and make it more robust in the future and create a lot of more and more information for the model's predictions. Expansion to this method for new clinical and non-clinical domains. Apply the methodological pipeline to other clinical relevance microorganisms, for example, and other areas also. Integration with other state-of-the-art model and just maintain the application updated with the current models in the state-of-the-art. And important step here, optimization of the shine symbol for real-time performance. Explore more efficient alternative to replace the SHAP method because your time to make your decisions. Modal diagnose models make a fusion of the nose data with other modalities. Chuck has clinical metadata and imaging also and the usability and clinical adoption of the shine, make the validation of the final system with physicians in a real clinical environments. And is our reference used for this presentation. And here we have a paraphrase of our Turing article. The imitation game has a basis. And he said, he wrote in your paper, in the first line of your paper, I propose to consider the question, can machine think? And I add a little contribution for this question, or smell. I think in our case, we can show that the machine can smell and identify patterns and maybe in the future help people um, to go home with health and to stay in home with your family with health and enjoying your your family. Okay, and I'm finished. Thank you so much everyone for your time, and I'm open to your contributions and your questions. Not neither of questions, but if you have just contributions, you'll be better for me. Thank you so much.
Primeiramente, desculpa, eu não sabia, não foi eu que fiz essa vez, foi sozinho. Eu achei que era machinário e apareceu
Isso
sozinho.
aí é porque não estava ligado ali no áudio, aí
Talvez tenha desbugado, porque eu desliguei o geral. Não desliguei só do YouTube, desliguei do geral.
Não tem cuidado não.
E aí ele entrou, assisti você um pouquinho, o pai entrou também.
Agora?
Foi sair, você fez essa coisa não, né? Aí ele disse, como hablas? Ai, pronto, tá legal. E eu pedi um remédio, eu saí naquela hora, porque eu pedi um remédio, a mulher disse que. Eu só quis perguntar o preço, aí eu pedi pra entregar, pra você entregar na gratuito. Gratuito, ela disse que não. Eu disse, "Oxe, por que tá entregando na gratuito?" Aí de repente chegou um panador aí, de pirona. Eu saí pra pegar. Aí ele, alô, pois é da farmácia, eu tô aqui buzinando, só que ninguém sai. Eu digo, oxe, mas não sabe, porque a mulher não finalizou a entrega, por isso que eu não fiquei atenta. Aí pedi desculpa a ele, mas pronto. Ele tomou lá na dor.
Deixa eu falar do YouTube aqui. Sim, quando eu terminar, eu vou ficar assim, eu vou só mudar aqui, ó, pra, pra sala, eu vou ficar aqui, de boa. Aí tá transmitindo isso aqui, né? Aí se eles precisarem de alguma coisa, fala, ó, slide tal, aí, aí já tá o slide tal aqui, ó. Aí direto. Legal, né?
Eu gosto dele. Ai, eu também da filha, gostei.
Aí lá só não dá pra ver a filha, só dá pra ver a apresentação, né? Aqui no. Cadê?
Aí, quando eu vejo as fotos de Helena, dá uma calmaria.
Sim, cadê? Ué, aqui. É isso.
Legal.
Deu pra ouvir bem, né? É,
Ouvi?
sim.
Eu não ouvi, eu deixei mudo.
Não, mas quando tu tava vendo, porque
Da
tô
outra
usando esse
vez?
microfone aqui, sim.
Não, daquela outra vez que você fez que eu tava lá, eu escutei perfeitamente. Jô, você já tava com o microfone? Daquela
Tá,
vez?
tá.
Então tá bom. Vou começar a fazer mais live então agora.
Pois, thank you for everyone. Bye bye. See you tomorrow. And God have. Como é piedade, não sei falar em inglês. God, that the Lord bless me tomorrow.
Eu posso mandar essas coisinhas pra terminar?
Pode.
Vou mandar os parabéns, assim. Tchau. Posso sair?
Tchau. Tchau, 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 tchau. Ai, meu Deus, não se mua.
Calminha, gata.